All right, so now that we have a function that gives me all the prime numbers, well, let me just try to use it to get lists of prime numbers until, let's say, a large n, right? So I'm going to start logging how long it takes. I'm going to see how long it takes. As always, I'm going to say import, say, time. And I'm just going to do two snapshots here. So t naught is equal to time, say time, you know, time dot time. So that's kind of a snapshot of time before I call this function. I call the function, and let's say maybe I just call, let's say L is this list, and I just then, so t1 is equal to time dot time once again, and I'm going to just print, for example, a few things here. Say L, um, so L is I think too much. Say maybe len of L, so how many prime numbers there were, and say t1 minus t naught. So that's going to tell me, well, look how many prime numbers there were in this list, and basically how long did it take. So let's say until 50, if I were to do this. So there are 15 prime numbers and it took this long, right? Again, it's fun to do this for, let's say, for different values of n. So what I'll do is to start with 100. Let's get all the prime numbers. Let's see how many there are. So it's 25 prime numbers until 100, and I got them quite fast, 0.0001 seconds. Interesting to notice, however, that 25 numbers are prime in the first 100, which means 25% of numbers until 100 are in fact prime numbers. Very dense. If I were to make this, let's say 1000, so clearly I expect the numbers to increase. 16% of numbers are prime now, 16.8%, 17% numbers are prime. Running time did not change all that much. Quite good, not bad at all, right? So if I were to go further, say 10,000, I notice that, well, it's 1,002 to 9, so roughly 12% of prime. Running time is kind of increasing a little bit, but not bad, manageable still, right? So if I were to go further, let's say one more zero, when I run this now, there are 9,592 primes. So that's approximately 9.5% of numbers are primes. So you notice that density is reducing. First 100 numbers had 25 primes. Now first 100,000 numbers have only 9,000 primes, right? So, and it took us, let's say, approximately, um, you know, um, this has taken me 0.14 seconds, not bad. Now let's say I add one more zero to this. So still quite okay. When I do this, now there is some work happening. You can see it's going into a few seconds. In fact, it's 78,000 primes. It has taken us approximately 4 seconds to do this. So clearly the time is increasing. If I were to do this, say one more zero, right? So if I were to do this one more zero, we realize that the running time really, really goes to the roof, right? And that's when we start asking question. Um, is our approach really smart? Yes, we had a smart function to figure out a prime number, but is this approach itself smart to get all prime numbers? In fact, a little bit of thought reveals that it's not, because think about it, right? The way I'm checking this right now, I'm checking every number between 2, 3, 4, 5, 6, 7, 8, all the way to n minus 1 if it's prime or not. But in fact, I know it for a fact that look, 2 is the only prime. Apart from 2, any other even number to be is not to be tested, because we are really just wasting time, right? Because we know it's not a prime number. Likewise, we know that 3 is a prime. However, all multiples of 3 are in fact not prime. Similarly for 5, similarly for 7. The point I'm trying to make is that this running time, that which is now over, let's say 1 minute, it's 1 minute 20 seconds right now. It can be reduced if we are a little bit smart about it. There is no point in checking for numbers which are multiples of known prime numbers, and that way the runtime can be dramatically reduced. Now that is what leads us to what is called the sieve of Erothethenes. That's a nice bonus to build. The idea is that to start with a, let's say, a sieve. You basically, instead of focusing on the prime numbers, you focus on the composite numbers. For example, all multiples of 2s, all multiples of 3s, all multiples of 5, all multiples of 7, and so on and so forth. Basically, all the composite numbers you can think kind of drop through the sieve. What remains are the prime numbers. In fact, that is going to run a lot faster than this. By the way, it has taken us 124 seconds, almost 2 minutes to find. Well, lots of primes, no doubt. 664,000 primes. In fact, a lot of primes indeed. But this algorithm can be speeded up by using what is called a sieve of Erothethenes. I'm leaving that as a bonus for you, as an exploration topic for you. But let's just summarize this. So when we ran this algorithm to find the list of primes, let's say for 100, 1000 and so on and so forth. Initially was quite okay because it ran really fast. But as the n became large, the runtime started to scale and became quite a lot, right? So it's like 124 seconds. But more importantly, once again, is this smart? I mean, is this doing the work that it needs to do? In fact, the answer is not if I approach it differently. Like I said, the sieve of Eratosthenes is the right way to look at it. Basically, the idea is that focus on the composite numbers and everything else remains prime, right? So seeing the same problem differently can lead us to a better algorithm, which is, like I said, a recurring theme of this entire course. Before wrapping up, however, let's make some observations about prime numbers in general. Basically, we realize that the number of primes becomes, let's say, thinner, right? So, what I mean by this is in the first 100 numbers, 25% of primes. But if I look at the first, let's say, this large number, whatever it is, this is 10 million numbers, only 6% of them were prime. So in fact, prime numbers kind of thin out as we go deep, let's say larger and larger numbers. So finding them can actually going to be harder and harder in some sense. Another interesting thing to notice is that, look, the number of primes itself increases approximately by a factor of 10. And remember, for these prime numbers, the smart algorithm also ran root n times, right? So which means that I kind of expect the amount of work to be increasing by 10 times square root of n, n times square root of n, which is 10 times square root of 10, which is 30. Not exact, but kind of in the order that we are seeing. Kind of, right? So, that's the point that we're trying to make, that look, the algorithm now, this algorithm is naive because scaling as n times root n, where n is the number of primes. So it's n is not this n. This number, obviously, the percentage of primes is very small with large numbers, but still it scales as an n root n. For large n, it becomes kind of large, right? And sieve of Eratosthenes makes it much, much more efficient. Do explore that as a bonus. Happy to discuss. But I hope you found this interesting. I hope you're getting the intuition as to why making algorithms smart, making algorithms efficient is important, and how the scaling of the algorithms is actually starts to matter when the numbers are large. Algorithms are the central focus of the YByte Algorithms and Olympiad track. Look at our website www.ybyte.in to learn more details. And remember, forever enjoy coding. Take care. Thank you so much. Bye bye.